My name is Nicolai Josuttis. I want to talk about C++ 17. One reason I talk about it, I think there's a little bit of a feedback loop if you lower the audio a little bit. Do you hear that? Yeah, thank you. So, just before we start, I'm curious. Who thinks she, only he here, at least here in the room, high out there. Who thinks that you have understood everything in C++? Nobody, okay. Who has a recent clue about C++? Okay, let me phrase the question differently. Who's programming in C++? Oh, they raise all the hands, so that's it. Okay, that says something. And I'm in the same position. The only advantage I have, I'm standardizing C++, or I'm helping to standardize C++ for 20 years now. And I think I have, you might have seen my books. Can you reduce the audio a little bit? I think it's loud enough. Okay, thank you. So you might have seen my books, and what else should I say about me? I'm self-employed, and maybe I'm one of the few application developers in the community. That's probably not a fair statement, but to some extent, our problem we have right now is that we are far too many experts, experienced C++ programmers, and sometimes we are surprised how people use our stuff and how few things they know. And so I want to try to present you C++ 17 here. And we start with, it's 2 talks. The first talk is about the language features, and then after the lunch, there will be a talk about the library features. And I will focus not on the details, but on the ideas and how to use the ideas. So application programmer's view. That's it. Okay, let me tell you a little bit about C++ as a general version and C++ 17 as a general version. After C++ 11, we went to a 3-year schedule. So every 3 years, we want to have a new standard out. And it's a time box approach. That means whatever fits in C++ 17 is ready to be delivered. We ship it, which, by the way, caused some reaction because a lot of things were expected in C++ 17 that didn't make it. So I think, so some people are really asking, is C++ 17 worth it? But as you will see, I would say this is a medium new release, and the medium means that we got a lot of minor features, which you have problems to talk about in a whole day. And so this is definitely more than C++ 14. And as I said, I will cover the most important things of it. So first of all, let me also talk about support. The good news is that C++ 17 will be supported or is supported already in major compilers. So GCC G++ 7.1 is released 4 weeks ago, I think. They support all core features and many of the library features. We have Clang 4, which supports most of the core features. Even earlier versions support some of them. And Visual Studio 17 also supports some of the language features, but they will have updates this year supporting most or all of the features. So at the end of C++ 17, I think 3 major compilers will more or less support C++ 17 completely, and that's good news so that you can use it. Yeah, let me skip that. So let's start with the language features in one feature after the other. The first feature I want to introduce is structured bindings. You see here in an example, the idea is that instead of initializing one object which has multiple elements, you can initialize multiple objects which represent the elements. So you see here that I have a structure taking an integer and a double, and if I assign this structure to an auto uv, then u and v are representing the members of this structure. What is behind the scenes here, the reality is that this declaration creates a new object. So you copy ms to a new object, and u and v are just names for I and d, so the elements in the new object. So, and all rules follow from that. So there's a hidden object which you can't access directly, but you can access all the elements in this object. And that works for structures. So especially if a function returns a structure, you can directly assign these return to members of the structure to different names. And it's an error if the number of elements or members doesn't fit. You can return an array and can assign the array elements to names, to a new object, which is a name, with a name. And then you can also use that for any object that has a get interface, which was introduced with tuple, and which, for example, also applies to std array. So if you have an std array of 4 ints returned by a function, you can directly assign it to the names I, j, k, and l, which is you return a new array, it's a copy, and then I, j, k, and l are names for the 4 elements in the array. You can also use this with tuples, so then you even have a heterogeneous result, heterogeneous assigning to A, B, and C, a character, a float, and an std string. That helps in a surprising amount of code. Here's a simple example. If you have a map of string and double, and you want to iterate over it, as you probably know, if you iterate over a pair, and the elements of the pair are named first and second. But this way here, you can do things differently. You can declare a const autoref this time, so that we don't create a new copy, but that we just have a new object which is a reference of the element, and then directly say that key and val represent the 2 elements in the pair. So instead of using first and second, you can directly use key and value, which makes the code far more readable. And the same is, of course, true if you want to, for example, iterate over the elements and modify the values in the map. So, next feature. We were so surprisingly happy with the new for loop, the range-based for loop, that we decided to extend the other control structures we have. So now we have initializations for if and switch. So if and switch no longer only take a condition, they optionally take an initialization. And here you see some examples that work with that. If you have a check like is S successful or not, you can directly transfer this to one statement by saying if status S equals check and S not equals success. And the S you initialize here is available until the end of an optional else statement. Which you can, for example, use if you have a lock guard. So if you initialize a lock guard and do some checks, you can do that now in one statement, and you don't need additional curly braces because at the end of the if statement, the lock is gone. By the way, don't forget to give this lock guard a name. If you don't give it a name, it's a temporary object, and the temporary object goes away after initialization. So that's not what you want. So don't forget this name, LG here. And the same is available for switch statements. So one of the things I'm trying to check is what happens if we combine different features I introduce here. So here's an example. If we combine the new feature of the new if statement and the structured bindings, you can improve code like this a lot. So guess you want to insert a new element in a map. the element has a string and a value, then you might know that the return value is a pair where the second part signals whether it's successful, and the first part is then explaining why it wasn't successful. So you get the details of an element that was already there. So this is the code you usually write then, or you might even worse, write something like using red dot first, arrow first, and nobody can understand that, at least naively, not knowing the exact details of the interface. That way, we can do it easily. We can say, well, let's first initialize a structured binding of person done by the return value of insert, and in the same if statement, check whether done was successful, whether it was done, and if not, let's initialize a temporary element with the first element there, so with the position, so that we have key and value, and then we print out key. And again, this reads a lot better than before. New feature, inline. If you program in C++, and a lot of times you are wondering why I have to use just a CPP file to define a global object. Anything else could be in a header file. But the rule is, if you have a global or static object, to initialize it, it has to be initialized in just one translation unit. And therefore, you need one additional CPP file. That's gone. You can now completely specify libraries in header files, including all the global and static objects of the library. And the trick is to use the keyword inline. So here's an example. If you have defined your own monitor class and you want to declare a global monitor object, you can do everything in the header, just declare the object to be inline, and then all the different translation units can include this header file, and that's it. And if they use proc monitor, the global object, it's the same object in each and every translation unit. So that will help to write libraries just as header files a lot. Next thing, we extended the idea of what is an aggregate in C++ 17. So now we have the ability that aggregates can have public base classes, which initially I think was driven by the idea that, for example, you might have a C++ class extending a C structure. And that's a typical application where you have that. Here you have another example. You declare a structure D deriving from string and complex. Oh, well, this was possible before. But the new thing is that this is an aggregate. And that means you can use aggregate initialization here. So you can have list initialization with the curly braces, and you can have nested list initialization for the members, for the classes where you derive from. So we initialize here the string of the base class we derive D from, and pass in the second initialization list, we pass two elements to the complex, which, by the way, is still templified. And then the third element is the initialization of the members. So you can then use the usual way. This is nothing new to deal with that aggregate. And we have a new type trait checking whether something is an aggregate, not only for these reasons, but also for some other reasons, because there are sometimes special rules for aggregates. And if you want to write generic code, aggregate is helpful. Next thing, we have now mandatory return value optimization and copy elision if you have a PR value, which more or less can be translated if you have temporary. So that has an interesting consequence. You now can create a class that's not allowed to get copied and not to move. So you can't do anything with it. after you create an object, you can't pass its value to another object by copying or moving it. But this is no longer true. You can now still return it as a temporary object. So if your function creates an object of this class, because now return value optimization is mandatory, now no copy and no move constructor is needed. So this works, and the same applies to assignments. So if I then assign this return value to another object, this still works. So we now require that this optimization happens, and therefore we no longer require in these scenarios to have any copy or move support at all. And the same is true if you pass an object as a parameter from a temporary. So if I create a new object or I return it from foo, which we defined above, I can directly pass it to another function, and that's still allowed, although no copying is possible. Of course, it's not possible if you have an L value, so an object already, and it should be copied. That's no longer true, as it's not possible to pass an STD move of X here. Of course, we extended the usage of Constexpr everywhere. And one example is lambdas. Lambdas are now implicitly Constexpr if they can. So here's a lambda taking the square of a value. It's a generic lambda, so taking any type and returning its square. And you can do the following now. You can say, I want to initialize an array of ints with a squared value of 5, and what 5 can come from anywhere where you compute the value at compile time. Because this lambda, by definition, implicitly is now Constexpr and can be used in Constexpr expression, which means it can be used by the compiler at compile time. You can signal that you want to have this at compile time to double check whether it's possible to use it at compile time. So if you there place Constexpr, the compiler will complain if you do something that's not possible at compile time. For example, if I have a static object inside squared, then this is not allowed to be, or this is not available at compile time, and so this is not allowed to be used in compile time context. So this will be a compile time error then. Just the declaration of the lambda will be a compile time error. We have some small things, new attributes and new rules for attributes. For example, no discard and maybe unused and fall through are some of the things some people already had at lint. For example, fall through were case statements without a break, and no discard may warn if you are not using the return value, and this is, well, at least strange. Well, I should say it's more than just strange. It's usually a programming error. So usually no discard we would place where a function returns a value you explicitly have to free. And then no discard is now a requirement that the compiler complains if you don't use the return value. We have new places where we now can use attributes. For example, we can, for individual values of enumeration, say these are deprecated. And we have also a using declaration, which is in general allows that attributes can have a general statement so that you don't have to qualify all the things you want to use in an attribute, which is, there's nothing useful for that in the standard attributes, but if you have your own defined attributes, this might be helpful. And another small fix, if you have nested namespace, you can now write them as one statement. Everybody who does that knows that this is some improvement. We introduced with C++ 14, we introduced the ability 14 or 11, I'm not sure actually. We introduced the ability to align data. Oh, I think it was 11. So you could say align as, and that means that, for example, in a structure, you can ensure that your integer in the structure is aligned on a on a 4-byte address, 4-byte aligned address or so. This was used and respected if you created objects on the stack, but not on the heap. And this is a solution now for the heap. So the problem was that this means that we need new operators, because now, as you can implement new yourself, you might have an additional argument telling you the requirement regarding alignment of this object. So this will extend the existing new interface. If only one of them provided, it will be used by default in all cases. So that your code is still backward compatible. And finally, as a feature, has include. So we have in practice this problem that in a preprocessor, we want to include something, but we don't know whether it's available. And so we can now program to try out, by the program, different header files. Here you see the example. If we have an optional, then we include optional. Otherwise, if we have experimental optional, then we include experimental optional. Otherwise, we do something else, which might help to deal with the fact that environments have different states of new features or libraries or versions. Okay, so far for the core features without template. Oh no, two others I have, sorry. I come back to what I just wanted to say. So we have now UTF-8 character literals. You can define them, but it's not a trick to extend C++ code to support fully UTF-8 code characters. It's just supported for those characters who are representable with a single code unit. And we have hex. OX also now supported as a prefix for floating point literals, so you can do the things you see here in red with some rules behind that. If you know that, it's already supported as output by the SCD hex float manipulator, and it's also coming from C99. So this is now possible. If you're in the science area, you might need that. So, as promised, that were the language features without templates. Now we come to templates, and as we all know, there's a hidden statement that C++ is the generic language. I think when you look in the standard, probably 99% of the standard features are templates. And so we support a lot of things. And of course, this support grows now with C++ 17 in a couple of interesting directions. So let's talk about them in the second half of this talk. The first thing is, we have a compile time if now. That means at compile time, we can say whether we want to have this compiled or not, and whether only the first half or the second half, so the then part or the else part, is used in your program, and whether that corresponding code is generated. That doesn't mean that the non-generated code, the so-called discarded statement, is not checked in any way. The rules apply as for templates in general. So in general, if a template's not used, still some checks are done with it. So we call this the definition phase checks of dealing with templates instead of the instantiation phase, where we know how the template parameters are substituted by concrete types. So the first phase also applies here. So that means if we have code here that checks if std integral, if a pass t is an integral type, then we recursively call ourselves with one less or so. Then the else part, even if t is integral, is still considered, and then it depends on the usual template route. So as here, undeclared is depending on the template parameter, it will not check whether undeclared is available, because it depends on the template parameter. But if you have a declaration that's not dependent on the template parameter, then you will get an error if this is a problem. By the way, I should say that this two-phase compilation or two-phase transformation of templates is not supported in all compilers. Visual Studio doesn't support it yet, or they now support it with the next update of Visual Studio 17, and a couple of code might break because of that, because suddenly the else part is not just declared, or in old templates, a template is not ignored, code is not ignored, no longer ignored. Some checks are done, especially for everything that's not depending on the template. So that will change with Visual Studio 17. It's already in the other compilers, and that also applies here. So everything is checked except the things that depend on a template parameter. So a common error and surprise will be if you have a static assertion saying, now when I come to here, I signal assert false. So compilation will fail with a message like no integral. This will always assert, always, independent from whether t is an integral value or not. This, by the way, will also happen now if you recompile your code with the new Visual C++ 17 feature, because in general, in template, this is a rule. And so if you use a static assert, you have to make it template dependent again. So you have to reformulate the assertion to check whether it's not integral, and then it will work as expected. Okay. You can even use if Constexpr in functions that are non-templates. Then all the rules apply, which I just introduced, except those where code depends on template type. So it just means that we have the checks for whether the code is valid, whether it has a correct syntax, and for each and every function called, it's checked whether it's available, even if it's part of a discarded statement. So even if numeric limits on your platform are not signed, if you haven't declared undeclared, this will fail. And again, if you have an assertion with false, this will always assert. So it follows the same rules as before, but we don't have any template depending parameter. So having said that, these were just some warnings. So this is an incredible helpful feature. It will resolve a couple of places where we just overloaded different template functions or did class template partialization, special partialization, just because we wanted to have different code compiled. And now we can do it in a function internally if it doesn't affect the outer interface of the function. You can do, for example, this. This is old C++. So it was a variadic template saying, I want to print the elements, the passed elements, and it could be one or more elements. So I pass a first argument, and then an unlimited number or variadic number of additional arguments. And the trick was I printed out the first argument, and then I called myself again for the remaining arguments. So I called me recursively myself, always printing the first element, and then calling myself for the remaining elements. And if you try that with just an if, because you can check for the number of remaining elements, this didn't work because this was not a compile time if, this was a runtime if. And so the code the compiler tried to compile here was to say, well, even if I have no remaining arguments, so if the if statement here results or yields false, I still generate code that print without any argument should be called. And if there is no print that ends this recursion, this couldn't work, or the compiler rejected to compile it. So this, for example, now can be changed into if Constexpr, and now things work as expected. By the way, there's a funny story behind that. The feature is called Constexpr if, but it's written if Constexpr. It has some historic reasons, and there's also the idea of explaining it by saying, well, This is the Constexpr version of the if statement. You can read it that way, but if you write it, it's the other way around. So we have some confusion, but it's not the first time we have confusion in C++, I think. So if you want to recursively deal with some arguments, variadic arguments, there's even more. There's a so-called fold expression. And the fold expression is an implicit recursion just in one statement. So if you have a variadic number of values of type t, and you want to add all these arguments, instead of doing the trick I just showed you, so recursively adding just the next element and then call myself again, I can use a fold expression. And it's parenthesis, dot, 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 an operator, then a parameter pack, and then parenthesis. So this is the whole expression. You have to use the parenthesis here. And this expands to apply the sum operator to all the elements, or if you have an additional initialization, like in the second example, this applies that you add all these elements to 0. And that way you can do a lot of incredible things and simplify your variadic template handling, as you will see. So here's one example. We can use this fold expression for almost each and every binary operator. So for example, this is using this for the member pointer, so for the member pointer operator. So guess you have a node type, and inside the node, so it's for a tree, it's for a binary tree. And the elements in the node refer to the left and right child of a tree. And there are convenience names like left and right, which represent these left and right data members. And then on the bottom, you initialize your root with a new node, and then you assign to the left, as a left child of the root, a new node, and then to the right side of the left side of your root, a new node. Then you can call traverse, and well, it's easily readable. So traverse from root, left, right, and return the corresponding element. And the trick is that traverse now is no longer a recursive statement. It's just a fold expression following all the paths with the arrow star operator. So some cool things are possible here. And fold expressions also work for types or for expressions that use types. So here's a very condensed way to check whether all my elements in this template are homogeneous. There are other ways to do that, but this is just one way to do it. And that means if I pass an element of type T1 and then additional elements of type Tn with different types, this return statement checks whether this type T1 is the same as all the other types. And how is it worked? Because if I pass 43, so an integer, and then -1, another integer, and then a string constant, and then a null pointer, then this expands to it calling is same for the first element, so 43, with, or the type of the 43, with all the other elements. So that way we can very condensed check whether things have the same type. I think you got an idea of this feature. How can we use that? Our print example we just introduced, where I showed you compile time if, can be now even be better improved. You can say, I want to print all the arguments. I no longer need recursion. I just use a fold expression. So saying, when I want to print 7.5 hello and an std string world, I use a fold operator to write out all these elements one after the other to see out. I can do that. The only problem is no spaces are between. So I need some tricks. So I need an add space applier here, which can be part of the fold expression. So if I have a helper template, taking an object and introducing the output operator for it with an additional space, I can now use this add space argument or helper template to use it in a fold expression to print out all the path elements with the space added. And of course, you can templify what you want to add there after the argument, so you could use something different or a parameter for that. Please look at the red add space statement. Look very carefully, because we now go to the next statement, which is it's not necessarily anymore required to pass templates, to define template parameters when you create an object of a template class. We call this class template argument deduction. So whenever we have functions, template parameters are derived from the passed arguments. So the question was, why can't this work for class templates? And the answer is, it can now. So in the past, when we created a complex of integers, which is not always supported, by the way, but which is in principle possible, then you had to write complex of int and then the values for initialization. But now we can skip the int with C++ 17 because the fact that this complex is instantiated for int is derived from the fact that we pass two ints here. And if we pass two doubles or floating point values, this will be a complex of double, of course. And that works with both with the old initialization way with parentheses and with the new way using the curly braces. Complex is defined as taking one argument t. So you see it on top, template type name t. So the compiler has to be able to deduce this t, and if there's contradicting information, if there would be type conversion required, this will not work, as it would not work for functions. So if you pass 5 as an integer and 3.3 as a floating point value, this will not compile. And here's another example, also very helpful. If you have used lock guards already, it was always nasty, because if you had a mutex and to initialize a lock guard, because lock guard was a class, you again had to write lock guard of std mutex, which is now, using this feature, no longer necessary. This is not a very trivial language features. We have a couple of interesting things to discuss here. The first thing is, sometimes deductions are not possible or do strange things. Excuse me. And one feature we have for this is we can formulate deduction guides. So that we say, instead of the compiler, here is our guide how to derive the class template parameters from the initial values. So here is an example. I could, if I'm allowed to, or if we would do that in the library, I could formulate to say, if I initialize a complex of two different types, for example, an integer and a floating point literal, then here's the rule. Please initialize a complex of the common type of T1 and T2. Common type is a type trait we have in the library, which automatically finds a common type of two types according to language rules, or you can also provide some rules yourself. So from a language rule, if you, for example, add an integer with a double, the resulting type is a double. So the common type of these two types is a double. So we will initialize here a complex of double, and it will suddenly work. Unfortunately, we don't have that in the library. So that's not supported, and you are not allowed to support that, because user-defined deduction guides must be defined in the same context as the original class. So if the class is defined in namespace std, also the deduction guides has to be defined there, which they are not allowed to do. But it works. I didn't tell you that. So, okay. But we have some deduction guides in the library. Some simple, some interesting. Here's a first simple example. If we introduce a container like a vector with two iterators. So what should be the element type of the vector? We can derive it from the iterator. It's a type, it's a value type of the iterator traits of this iterator. So there we can find the element type. So that's a corresponding deduction guide. We say when we initialize a vector by a type named iterator, because that's the semantic we have here, then we try to, for this type, to find the iterator traits and having then the value type, and that's the type the vector should get. So that means if I have a set of floats and I initialize my vector with begin and end of this set, then you no longer have to write vector of float, because according to this deduction guide, this will be deduced automatically by the compiler. And this is inbuilt in the library. Here's another inbuilt deduction guide. It brings together a couple of features I introduced already. This will look at the bottom first, maybe. This will deduce that if you initialize an std array A by 3 integers, that the array is an array of 3 integers. So it will deduce two things, type integer and the value 3, because an std array is a fixed size array. And how does it work? See the code there. We have a deduction guide taking one type and additional types. And then we say, by a trick which is used in the library a lot, that we only support this deduction guide if type T is the same as a type U and all the other type U we have, because this is a fold expression we use there. This fold expression, again, like is homogeneous we had before, checks whether all the types are homogeneous. And enable if says, if this is not the case, this whole deduction guide is not available and can't lead to any trouble. So if the types are the same, then we initialize the element, the array, by the type T, enable if T, then if it's valid, yields the type T, and then the second argument of the array is 1 plus the remaining arguments, because the first argument was for the T, the remaining arguments number is U. So in this case, size of ... of U is 2, and 1 plus 2 is 3. So this deduction guide works. This is also inbuilt in the library. Yeah, deduction guides don't have to be templified as you had it here. It's also just simply possible to say, I have a guide that if for a type S, a template type S, if I pass a string literal, please deduce S to be instantiated for std string. So now if I create an S without declaring the argument, the template parameter, in any case, S will be, std string will be deduced if I pass string literal. And that also helps if you deal with aggregates. For example, if you have an aggregate like here, there are a couple of language rules that allow more or less only one initialization, which is the second one here. But I can say I have a deduction guide, and now I have more implicit ways even to define or to deduce the type of an aggregate without specifying it. So here it is now possible to pass a string directly and to deduce that for this string, I want to instantiate this aggregate that the type T is std string. I skipped the other examples here. Okay. One more. Using declarations can now combine multiple elements. So instead of having 3 statements saying using base A, base B, and base C, we can now have that in one statement. And this was a side effect of the fact that we wanted to be able also to apply variadic templates here. So we want to have variadic template support in using declarations. This is a complete example. Maybe, let me look at the time. Well, maybe we have a little bit of time to expand on it or explain it. I have here a customer type, and I have two function objects. One creating an equality operation for the customer, and the other creating a hash function for the customer. And if I want to create a combined function object, having both the operator to create a hash function and the equal function, I can derive from both bases. Look there, overloader is derived from a variadic number of base classes. And for each and every base class, we derive the function call operator so that we have it available there. Yeah, but this is if you use that, you are probably already in the world of the tricky template programming gurus, but it's possible. Finally, for templates, we can declare now a non-type template to take auto. By the way, even decl type auto is possible, which has some strange consequences. So there's template auto saying, I'm not declaring what the non-type parameter n is. It can be an integer or it can be a character, depending on what I pass here. And this can't be used to extend the ability of templates, though. So you still can't pass a double here because it's not allowed to instantiate a non-type template parameter by a double type. Yeah, but it works. Let me skip that. So we have another thing. We improved over all the different C++ versions the support to write templates for string literals. When we introduced C++ 03 or 98, the first version we standardized, there was only possible by a trick to say, I want to instantiate a template by a string literal. So, because this string literal now becomes part of the template class. And the trick was you needed an external string with external linkage, so which is globally visible throughout the program. Therefore, you had to declare an extern const character hello, and then you could use it as a parameter const character star or char const star. Well, const character star is the general way to write it in a template. With C++ 11, we reduced this feature, and we said it's also possible if you have internal linkage. Internal linkage means it's not globally available, but it's available in my translation unit. So without the extern, but it still had to be global or static to some extent. So now, by definition, this has internal linkage. And now, with C++ 17, we have no requirement for any linkage at all. So that means that you now can declare a local static string and pass it to a template. So that helps a lot because now you can directly see that this template is templified for the string hello world directly in these two places there. And remember, we have auto now. We can do that with auto. So I can now declare a template taking an object of type t, which can be an integer, can be a character, but can also be a string literal if I pass a static constant declared directly before, which might also help or serve some needs. Often needed is this thing, for example, if you have some logging and you want to initialize a template by some information string representing the area you are logging here. So, what's the time? 10 minutes left. So now we come on the variadic part of this talk. The next thing is just a few core fixes and improvements. We improved a lot. We fixed a lot. Here's the first thing. I think the most important thing. Look at this statement. We have a string, and I want to replace some things in the string. I want to remove the first 4 characters. then I want to remove the characters even, and I want to remove the characters don't. Oh no, even is replaced by only. This is, by the way, an example Bjarne Strustrup has in C++ programming languages. And it turned out it's wrong. It's undefined behavior. Because the order of evaluation is undefined here. What might happen is the following. We first find the index of even and the index of don't. Then we remove the first 4 characters, and then we apply to replace the index of the previous position of even by only, which of course then replaces different characters. By language rules, this could happen, and this was undefined behavior. So we fix that. And by the way, another example that typically people make wrong. If I print out the result of a function f, g, and h, people usually assume that f is called before g. That's not correct. It might happen that g is called before f. So if there are some side effects between f and g, this is also undefined behavior. And we fix that. It's, by the way, because it does more or less the same thing as the example above, calling the dot operator. And the order of if you pass something to the dot operator, the order is not defined. So we have now a defined evaluation order for some operands. So dot, arrow, then all the ampersand equal operators, that's plus equals, minus equals, star equals, etc. The index operator and the output, the I/O operators. And the order, when we have an order of a function call, we don't specify an order now that for the arguments A, B, and C, they are evaluated in that order. But we specify that F, so the part before the arguments, is evaluated before we evaluate the arguments. So that's specified now. And that solves the problem above. And finally, we also had a very strange rule in the language. Look at this code and look at the statement, the second and the third statement above in the top area, A2 and A3. I think almost everybody of you would think, without having deeper knowledge, that A2 has type int. But that's not correct. According to the language rules we have in C++ 11 and 14, this A2 was initialized as an initializer list of int. And the second took 2 ints. So we fixed that because it did definitely violate the expectation of programmers. And now with C++ 17, this will be an int, so x2 on the bottom is definitely an int now. And if you pass multiple elements there, then this is an error now. Only if you use an equal sign, so if you use copy initialization, you still have the old behavior. This, by the way, again means that we have different behavior depending on whether we use copy initialization, so the equal sign, or not, so or direct initialization, which doesn't use the equal sign. So there might be a fundamental difference here. Yeah, but it's definitely an improvement. And finally, for static assert, it's no longer required to have a second argument than providing the string that should be printed, so the compiler has to find out how to print in the corresponding error message in the language of the compiler. We have 5 minutes left, so let's talk about one utility, just for the experts who are here. We have changed a feature called uncaught expected, and we have replaced it by uncaught exception. And we have replaced it by uncaught exceptions, plural. And instead of saying we are now dealing with an exception, you can check this, use this to find out how many nested exceptions do we have right now. Are we in, I don't know, in a nested third level of a throw statement or so? And here you see which problem this solves. Guess you have a class C, so the class here, which want to if everything is fine, commit something, and if not, roll back. So transaction safe class. And now you also have a class D. And the following problem happens. You create a C and a D, and then you throw. Well, then the destructor gets called of D. The destructor of D cleans up, and for cleaning up, they use, again, an object of type C. So they have the interesting behavior. If you ask them, are we in an environment of uncaught exceptions? Yes, because we are implementing behavior in a destructor. But still, using C here is fine. And so we do the following code you see here. We create a C and even another C in a try-catch block, and then we throw again, which is possible, but we catch that because the destructor should never throw. And that means that we now can find out that C2 should roll back, while C1 should commit. And that helps with the uncaught exceptions counter. In the destructor, you can find out that the number of uncaught exceptions has raised after the constructor, and that you can use to find out whether you should roll back or commit. Okay, so what was not voted in C++? A lot. And a lot of really new core features. I will tell a little bit about that in the next talk in the afternoon when I talk about the library. But as you see here, modules, concept, ranges, coroutine, reflection was not part of C++ 17. These were the big things we were expecting, and also some small things we were expecting were not adopted. So nevertheless, I think you saw already a couple of new features that help to deal with the day-to-day programming. And we have the same in the library, which I will explain after lunch. So tell you about the new library features. So I would say that C++ 17 is a significant improvement. It's not a revolution. The revolution will probably be C++ 20. Let's cross fingers here. No, not cross. What is the English word for it? Fingers crossed. Fingers crossed. So, yeah, okay. I think it's fingers crossed is when you lie. No, that's something different. Doesn't matter. You know what I mean. So let's hope that in C++ 20 we will have this revolution, and then a lot of things will change. But we have a lot of fixes that will help in day-to-day programming. The good news is compiler support is there. Try out GCC or G++7. They are online compilers. You can try it even out online. And Clang 4 or Visual Studio 17 with the updates that are coming this year. So there are also already pre-candidates that do a lot of it. And I can also announce here as an advertisement there will be books covering this issue. I'm involved into 2 books. The first one is I plan to write a book about programming with C++ 17. There's a website you can find details. And that's not exactly sure whether it will make it, but what we definitely can promise is there will be a C++ template second edition. So after all these years, I think after 15 years having C++ templates first edition, we now will have a second edition. And it will cover C++ 11, 14, and 17. And by the way, the book will have 800 pages just describing template features in C++. And it's necessary to have them. So this will be out in September when CPPCon in the US will happen. And we are still looking forward for C++ 20. That's it. Thank you very much. I hope this was interesting, and I think we have time for one question. Anybody want to question something or want to ask something? Okay, then enjoy. I'm around here, and what I can say is at 1:40 there's a second part of this talk talking about the library features, the new in C++ 17. Thank you very much and enjoy the conference.